Hi, everybody, and welcome back for Chapter 2. In Chapter 2, we're going to take a look at displaying data. So in Chapter 1, we talked about the basics of how data is gathered. And in Chapter 2, we're going to take a look at the idea of, okay, I've got data. What do I do with it? How do short of just handing a pile of data, whether it be numbers or words, if it's, some sort of categorical data, some qualitative data, or a pile of numbers if it's quantitative data. What do I do with it? How do I present the material in such a way that the reader can look at it and say, I understand what this is trying to tell me? Right. So in this section, we're going to take a look at the idea of frequency distributions as a way to organize data. And then when we have one of those, what we can do with that frequency distribution to summarize the data. Okay. Now, frequency distributions are usually when we're working with larger data sets. If you have a really small data set, if the data set is just small, and I'm talking like maybe up to about 20 values, and there's no hard and fast way to say below 20 is small and above 20 is big, but relatively small data sets, we often just give the entire data set to the reader because it's not large enough when it's a small data set to really be able to see patterns in the data. And we'll talk more about that later. Right? But we'll start by taking a look at one of the most common ways, and that's a frequency distribution, one of the most common ways to display data. Frequency distribution, also referred to as a frequency table. Frequency table is a little bit of an older way to talk about these things. Frequency distribution is more of a common way to talk about that. And what it does is it takes a data set and it partitions it across classes, also sometimes called categories, but more commonly referred to as classes, by listing all these categories or classes and the frequency of the data in that class. And so it's going to look something like this thing over here on the right, this thing right here. That's a frequency distribution, right? Or a frequency table. And what it has is it has a class, and that class tells the reader all of the data values that are represented by that range. So that first class being 1 to 5 tells me as the reader that this frequency right here of 5 means that in the original data set, there were 5 data values that fell between 1 and 5 inclusive. Okay? Inclusive means the endpoints are included. Right? So that means that in the original data set, 5 values were either 1s, 2s, 3s, 4s, or 5s. Now, what they were, I'm not certain. They could have all been 1s, they could have all been 4s, they could have been spread out. I don't really know. Right? Same thing is true with every other class. For example, this class right here is 16 to 20, and that frequency is an 8. Well, that tells me there were 8 values somewhere between 16 and 20, inclusive. Right? Now, it goes further. We have names. All of these numbers right here, those are all called lower class limits. So when I take a look at this, if I'm talking about this right here, the 6 to 10, then the lower class limit of the second class is 6. The lower class limit of the third class is 11, and then 16, 21, and 26, and so on. Now, if those left numbers are called the lower class limits, those ones on the right that is boxed out in blue are the upper class limits. So if I wanted to talk about this number right here, I could say the upper class limit of the third class is 15. Okay. Now, I'm hoping that when you look at these numbers, you see some patterns in here. What I mean by that is the change that exists from here to here is 5. The change that exists from here to here is also 5. The change that exists, 5. The change, 5. The change, 5. Do you see how it's consistent? It's always the same amount? That amount is referred to as the class width. It is the distance between lower or upper limits, because you could argue, hey, this is also 5, 5, 5, 5, and 5. Now, sometimes people will mistakenly think that, well, if that's my class and 5 minus 1 is 4, that means the class width is 4. That's not correct. Because if I look at that first class, just the first class is all the 1s, all the 2s, all the 3s, all the 4s, and all the 5s from my data set. And if it's all of those values, that's 5 values. Similarly, if I were to talk about this one, the second class, that's all the 6, the 7s, the 8s, the 9s, and the 10s. Again, 5 values. So we have that class width of 5. Right? All right, so I'm going to erase some stuff so it isn't quite so busy over here, because we have more to talk about when it comes to these things. Right? So I've got lower class limits. I've got upper class limits. I have class widths. I have frequencies for each class. Right? If I take the difference between the maximum and the minimum, I'm looking at the range. So one could argue that by looking at this distribution, there's the max, there's the min. So we could say that we have a range of 29, because 30 minus 1, the difference, subtraction, 30 minus 1 is 29. Okay. So there's a lot of information that we pack into this table, into this distribution, that's supposed to talk to us about the data set, right? Now, when I'm looking at just the frequencies and trying to gather information, what I'm noticing is these are the big numbers. So it looks like a big chunk of the data falls in here. And yeah, there's some data down here and there's some data up there, but these are the bigger numbers. So it looks like there's a big chunk between 6 and 20. And that's what a frequency distribution is supposed to do for me. It's supposed to give me a way to explore where the data is heavy, where there are lots of values, and where the data is light, where there are little values. And it's supposed to do that rather quickly. Now, I cannot get that same information by just looking at a pile of numbers. For example, look at this pile of numbers and tell me, how long does it take to get served lunch at McDonald's? I don't know. I can't look at that pile of data and figure out what's going on. So what I'd like to do is, with this much data, is I would like to turn this data into a frequency distribution. So let's take a look at the process. The first step is deciding on how many classes you want to have. It's usually some number between 6 and 15. Now, there is no formula. There's no way to say, for this many data points, use this many classes. It doesn't work like that. It's just 6 to 15-ish. Pick a number, see if it works. Build a frequency distribution. If you like it, you chose well. If you don't like it, choose again and do it differently. The next step is to figure out what the class width is. And the way we do that is we determine the range of the data. And remember, the range of the data is max minus min. And then we'll divide that by the number of classes. And then we will round up to the next convenient number. Now, what on earth does convenient number mean? Well, it depends on your data. You're going to round that makes sense with your data. So let's say that my data was the price of candy bars. And all of those prices were accurate to the penny. Then, when I was rounding to make my frequency distribution, I would round to the penny. I wouldn't round to the dollar because all of my data is in the pennies. Let's say that my data was prices of new cars measured in thousands, so like 28,000, 38,000, 45,000, numbers like that. Well, then a convenient number might be to round that class width to the thousands, because it wouldn't make sense to have a class width rounded to the penny when all the data is in thousands of dollars. So when we're talking about convenient number, it's what's your data look like, and then round appropriately. After you've decided on your class width, after you've found your class width, the next step would be to find your limits. Now, it is really, really common to use the lowest data entry in your data set as the lower limit of the first class. And then once you have the lower limit of the first class, you use that class width to find all of the other lower limits. And then you hop over and find all of the upper lower limits. At that point, you now have a first column here done in your frequency distribution. So then you need to figure out these guys. And unfortunately, there's no nice way to find those. We literally just have to go through and tally up to make those. Right? Now, the last step down here where it says modify as necessary, we'll talk about that once we get one built. The modifications that one could make to express the data in a slightly different way if you thought it was appropriate. All right, so let's go ahead and do that. We're going to make a frequency distribution for McDonald's lunch service times. And the way this problem is set up, they want us to use 5 classes. So we don't get to choose. We're going to use 5 classes. I know a moment ago I said 6 to 15 up here, but that's not even hard and fast. That's just sort of like, well, yeah, somewhere around there-ish. So we're going to use 5. All right, so now that I know how many classes, I'm going to move to the second step of the process, and I am going to find the class width. The first thing I need to do is I need to find the range of my data. Now, the range of the data is going to be the max data minus the min data point, right? So I'm going to dig into my table here, or my, I guess we'll call it a table, and I'm going to try and find the maximum and the minimum. Okay. Well, right now I got 280, 281, 308. That's a big number. Is there anything bigger than 308? I don't see anything bigger than 308. I think that's our max. I'm going to check again real quick. 222222221 200. I think that's our maximum value. Okay. Now I'll find our minimum value. I think it's going to be this 83. 91, 90. I think it's the 83 right there. Okay, so then my range is going to be 308 minus 83. So 308 minus 83 gives me 225. And now to find the class width, I'm going to take the range, divide it by the number of classes. So that's going to give me 225 divided by 5. So 225 divided by 5, and I get 45. Ha! Who would have thought it worked out nicely? Okay. Now, normally, usually, that's going to be a horrible decimal, and then we'd round. And given that all of our data is to the second, so these are all seconds, right? I would just round my class width to the second, but it looks like it's already rounded to the second for us. Right. Now that we've got our class width, we can start building our table. Now remember, our table is going to have 5 rows. Actually, let me do this. So these are going to be our classes. And these are going to be our frequencies. So that's 1, 2, 3, 4. I need one more. So let me make this a little bit longer for our 5 classes. Right? Now I'm going to start my first class by making the lower class limit be my minimum data entry, which is going to be 83. Now to find the rest of the lower class limits that go down here, I need to take that 83 and start adding on class widths. So I'm going to grab my calculator and I'm going to say plus 20, oh, wait, nope. Plus 45, because that was our class width. And so my I did that wrong. Sorry. 83 is my first, and then add that 45 class width, and I get that my next lower class limit is 128. So this is going to be 128. The one after that is just add another 45. So 173. And then the one after that is 218. Add another 45. And then the last one is 263. Add another 45. Now I'll go back that I've got my lowers. I'm going to go back and find my uppers. So the upper class limits for each of these are going to be a number such that it fits. And what I mean by that is, well, if the second class starts at 128, then the first class better end at 127. And if the third class starts at 173, then the second class better stop at 172. And then this one better stop at 217. And this one better stop at 262. Now, the tricky one is how do I find this guy down here? Because I don't have another class to subtract 1 from. But I seem to remember that each of these jumps from the first upper to the second upper, that's a class width of 45. So that last one down there, I could just take that 262 and add on that 45 and get that upper class limit is 307. Now you might be looking at this and going, we've got a problem. Do you see the problem? Let me go up a little bit so you can see the problem. Do you see the problem? What's our largest data value? Well, our largest data value is 308. And where does our frequency table stop? Well, according to this, it stops at 307. I mean, did I do my math right? Did I do 262 plus 45 right? So if my math is all right, how come this is wrong? Oh no. So something must be wrong with the math on this. And here's the issue, is even though this worked out right, we still have to round up by at least 1. And it's just this weird thing that happens with the math. So we really should have called that class width 46. And I know that it feels awkward to do that, but because of how we calculate the range as the max minus the min, and that's the right formula to calculate the range, we've actually eliminated one data point, essentially, from what should be included in there. And it's just this weird, wonky thing that happens with frequency distributions. So that means that every one of these numbers that we calculated is off just by a little bit. And so I've got to go back through and fix every single one of these, right? Now, what normally happens is this math right here doesn't work out nice, and you get something like 45 point like 45.6382, and then when you round it up to 46, everything is fine. This issue never shows up. The only time this issue ever shows up is when that math that we did, this 225 divided by 5, works out to a whole number. If it works out to a whole number, we have to add 1 to it. But it's a simple fix once you know what to do. So we're going to take that lower class limit of 83, and now we're going to add, instead of 45, we're going to add 46 each time, which makes the, got to get to a pen, the lower class limit of the second class be 129, and then 175, and then 221, and then 267, and then to find the upper class limits. This will be 128. This will be 174. This will be 220. This will be 266. And then that last one down there will be 266 plus our 46. And now we're at 312. I know what you're thinking now. Wait a second, that's too big. You're right. It is too big. Our data only goes up to 308. But there's no way around this issue. It's either going to be too small or it's going to be too big, and too small we can't have. So we make it too big. The next step is to literally go through and find all the frequencies, meaning I'm going to go through and go, okay, 107 is in this one. 139 is going to be in this one. And I'm going to walk through and tally up every single one of these. Now, you don't need to see me do that. So I'm going to pause the video and come back with it all tallied up. Okay, so I went through and tallied everything up. It looks like there are 13 here, 5, 10, 15, 20, 23 here, 9 here, 3 here, and 2 there. Right. Now that I'm done with these tallies, I don't need them anymore, so I'm going to get rid of them. Okay, now my job is to look at this frequency distribution and talk about how amazing it is. But more importantly, now I can look at this and say, huh, those two right there, that's where it is. I can expect that if I go to McDonald's and order, it'll probably take between 83 and 174 seconds for them to get my order to me. And while there is some data out here, here, and here, there's not a lot. Most of it is in that 83 to 174. And that's the whole purpose of a frequency distribution. I don't think that I could stare at this pile of numbers, and let me get the cross hatches out of there so it's easier to read. I don't think I could stare at that pile of numbers and tell you that most of them are between 83 and 174. I mean, that's a little bit over a minute to a little bit under 3 minutes. I can't get that by just looking at this data right here. I just can't do it. Right. So the purpose of this is just that. A pile of numbers is ugly, a table's prettier. Right? Now, there are some modifications we could make. Like, for example, I could turn this from a frequency distribution into a relative frequency distribution, right? Or a percent frequency distribution by saying that, well, instead of 13, because I don't know what 13 means, could I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, another 17, and a 16. So 17, 17, 16. 7 to 7 is 14, and 6 is 20. So 2, 3, 4, 5. So there's 50 data points. So could I say that this is 26%? And this one is 46%, and this one is 18%, and this one is 6%, and this one is 4% of the data. And sometimes, maybe this is how you want to present your data. So rather than giving these values, I would give those percentage values, right? And I might be able to look at that and say, oh, okay. I mean, this is, now I can look at it and say, that's 72% of the data. And 72% of the data is like 3/4 of the data. And I can get that information really quickly without having to look at 23 and go, okay, what is 23? Is 23 a big number? Is 23 a small number? 23 out of how many? Right? So when I take the sum of the frequencies and I see that I'm looking at 50 data points, I can turn those into percentages by just taking each frequency, dividing it by 50. I also could, if I wanted to, give the relative frequency, which instead of calling that 26, we would just say it's 0.26 and 0.46 and 0.18 and 0.06 and 0.04. So rather than representing them as percents, I could represent them as a decimal that is a relative frequency for that class. Okay? So a way that I can modify it is to turn them into either a relative frequency or a percentage frequency. Now, when you do a percentage frequency, the sum of the percentages should add up to 100%. It might not, depending on rounding issues. So we got lucky here. Someone gave us a nice number of data points that made all of those super easy to calculate, and none of them were horrible decimals that we had to round. But what if, and I know this isn't true, but what if this was a horrible data set with like 37 data points? Then all of those numbers would be terrible to calculate because we'd have to divide by 37, and then we'd have decimals and we'd round them. And even if you round correctly, when you added it all up, it might add up to something like maybe 99.4% or maybe 100.6% or something like that, where it could be a little bit off, and we would be okay with that because that's what happens when you round. When you round a number, you're technically making it a little bit wrong. And sometimes when you round and that little bit wrong gets added up, it can actually add up to a significant amount off, right? Another way that we could represent this, if we didn't want to do it that way, is we could make what's referred to as a cumulative frequency distribution. Now, a cumulative frequency distribution, and I'm going to make another column over here for that. If this was a cumulative frequency distribution, this would stay 13, but this would now be 36. Now, how did I get that? Well, a cumulative frequency distribution is a running total. So there were 13 in the first, there were 23 in the second for a grand total of 36. And now down here in this third class, we would add 9 more, so we're up to 45. And then down here in the fourth class, we add 3 more, so we're up to 48. And then down here in the last class, we add in the last 2, and so we're up to 50. So what we're representing here is, rather than straight up frequencies, which are in this first column, or percentages, or relative frequencies, we've got a cumulative frequency, which is a fancy way of saying it's a running total. Now, why would you care? Well, I don't know. But maybe the story that you want to tell to the reader is that they can look at that and go, there were 36 people who got fed in 174 or less seconds. There were 45 people who got their food at McDonald's in 220 or less seconds. So if that's the story that you want the reader to read, then you would use a cumulative frequency distribution. Now, none of these things are right. All of these things are just different ways that you can express the data. Okay. Good so far? I hope so. We're at 28 minutes, so I'm going to stop this video here, and I'm going to come back and start a new one right there, I think. Yeah, oh no, we only have a little bit more to do, so let's just finish this up on this one. Okay, gaps. What can a gap tell us? Okay, well, the presence of a gap could say there's something going on with the data. So let's look at this frequency distribution down here, where we have the weights of a penny and the frequency. And it looks like there's a bunch of pennies down here, and there's a bunch of pennies up here, but why are there no pennies? Whoops, wrong color. Why are there no pennies in here in the middle? Well, I don't know how much you know about coins or pennies specifically, but pennies made before 1983, the ratio of the metals in there was they were 95% copper and 5% zinc, whereas newer pennies made after, they flipped it, and they're only 2.5% copper and 97.5% zinc. So when they changed that, it effectively changed the weight. So what we're looking at here is we're looking at one population, and these are the old coins. They were mostly copper, and then a new population, a separate population, so a population 1, if you will, and a population 2. These are the new coins. that weigh more, right? So one thing that a gap can tell you is that you're looking at data from different populations. If there were several gaps, then maybe you have several populations. Okay. Now be careful, because just because a gap can tell you have different populations doesn't mean that different populations always cause gaps. Because maybe they could have changed the recipe down here and found a way to change it so that the weight stayed the same. Maybe they would have had a third metal, mix in some lead or something to make them weigh more or weigh less. I don't even know. But there's probably a way that you can make it so that it stayed the same. Okay. All right. Another thing you could do is you could map up two or more relative frequency distributions in one table so that we can compare data sets. And so what I have here is I have times and McDonald's versus Dunkin'. Right? And I have still classes over here. I still have lower class limits. I have upper class limits. I have class widths, the whole 9 yards. But now I've got two different data sets, the McDonald's data set and the Dunkin' data set. And I'm going to look at these percentage frequency distributions down here and say, it looks like I'm going to get served faster if I go to Dunkin' Donuts than I would if I went to McDonald's. 66, 2/3, 66% of Dunkin's customers are served in the same time that McDonald's is only serving about a quarter of their population. So if I had this data and I cared about time, I would say, get breakfast at Dunkin', or get lunch at Dunkin', or go to Dunkin' if you want to be served faster, because I can compare these two things directly, right? All right, so 2.1 is about frequency distributions. What are they for? Well, piles of data are ugly. I want a table. What does the table look like? Well, it's got to have classes to explain what I'm looking at, and it's got to display the data somehow. A straight up frequency distribution is just that. It is the frequencies of the data exactly what you want it to be. Right? A percentage says, maybe you don't like reading numbers and you want to read percents of a whole. Well, I can do that. That would give me my percentages. Maybe percents aren't what you want to give, and you want to give a straight up relative frequency, which is just a percent not written as a percent. Or maybe you want to give a cumulative frequency. Or maybe you want to do a side-by-side one so you can compare two data sets. There's no right answer. There's no wrong answer. These are just different ways that data can be displayed. And what we're hoping is that when you're looking at the table, you can gather information more quickly. Remember something though, we lose accuracy when we have a frequency distribution. Even something as accurate as this guy, where the class width is only 0.1 grams. That 18 tells me that 18 pennies are in that range, but I don't know how much any one penny weighs. I just know that 18 of them weigh somewhere between 2.4 and 2.49 grams. Okay? So we lose a little bit of accuracy, but we gain a little bit of clarity. All right. That brings us to the end of section 2.1. Next video will be 2.2. Have a great day.